Welcome to the video for Lecture 17, Section 1. This video is an introduction to Wheatstone bridge circuits. As we did before, I will present more development and background materials than you will need to do the problems for this section. And as we did with the transfer functions for the different processes, you didn't need to develop the transfer function for the processes. You just used the appropriate equation instead. Similarly here, you won't need to develop the Wheatstone bridge circuit equations. Instead, you will just use the equation that is in the course packet. The purpose of the Wheatstone bridge circuit is to convert resistance changes into voltage changes that we can measure with data loggers and PDAC55 units. The PDAC55 units cannot measure resistance. Wheatstone bridge circuits can be used with any sensor that has a resistance change. We will use Wheatstone bridge circuits with strain gauges and resistance temperature detectors. They both produce resistance changes in response to strain and temperature respectively. Here is a sketch that shows a Wheatstone bridge circuit. Let me explain the elements of the circuit. The four rectangular boxes represents four resistors. They are numbered 1 through 4, going clockwise and starting in the upper left side. So the circuit has four resistors numbered 1, 2, 3, 4. In many cases, we will assume that resistor 2 is the one that changes if only one resistor changes. In that case, the other three resistors, 1, 3, and 4, are assumed to be constant. Off to the left is the supply voltage, labeled Vs. In the center of the square is V0. V0 is the output voltage. This is the voltage that we will measure with the PDAC55 unit. If you compare this Wheatstone bridge circuit to other Wheatstone bridge circuits in other textbooks, you will find that they are not exactly all the same. Some diagrams have the supply voltage in the middle of the square and the output voltage on the outside. For our analysis, we will use Ohm's law, which says that the voltage drop across a resistance is equal to the current flow in amps times the resistance, which is V equals I times R. We will also use Kirchhoff's voltage law, which states that the sum of the voltages around a circuit loop must sum to 0. Using Kirchhoff's voltage law around the loop, including V0, V2, and V1, we get that V0 equals V2 minus V1. Then by using the concept of voltage dividers, we can write the voltage drop across R2 in terms of resistor 2, resistor 3, and the supply voltage. We can also write the equation that gives the voltage drop across resistor 1 in terms of resistor 1, resistor 4, and resistor supply voltage. And the supply voltage, With the equation for V2 and V1, we can substitute them in the equation V0 equals V2 minus V1. After making the substitutions, we get the equation shown that gives V0 shown below. We are going to use this equation multiple times during our discussion on Wheatstone bridge circuits. For a balanced Wheatstone bridge circuit, the output voltage V0 is equal to 0 and the output current I0 is also 0. And if the supply voltage Vs is not equal to 0, then the terms in the parentheses must be equal so that the difference equals 0 for the output voltage equals 0. Now if we solve for R2, we get the equation R2 equals R1 times R3 divided by R4. This simple expression can be used to measure how R2 changes by adjusting R3. Unfortunately, we need a way to know how much we adjust R3. This is not so easy, so balanced Wheatstone bridges are not used very much. The more common approach is to use unbalanced Wheatstone bridge circuit, where V0 is not equal to 0. We will talk more about unbalanced Wheatstone bridge circuit in the next video. This brings to the end of Lecture 17 Section 1 video. Please write down any questions you have and bring them up in class or lab.